In this video, I'm going to talk about the breadth first search for tree data structures. Now, the breadth first search of a tree data structure searches the breadth of the tree. So it goes really wide really quick. This is unlike the depth first search of trees where it goes really deep really quick. So to show you an example, if I create a small binary tree here real quick, something that might look like this, 1, 2, 3, 4, 5, 6. The breadth first search, the way that this search algorithm will traverse through this tree is first it's going to look at this element 1 up here at the very top. And then after that, it's going to look at elements 2 and 3. And then after that, it's going to look at elements 4, 5, and 6. And so it's going to sort of explore this thing down level by level by level and get deeper and deeper, right? With the depth first search, it kind of shoots down one side of this looking for a value as fast as it can, trying to get to the bottom as quickly as it can. With breadth first search, it goes really wide, really quick. So it's going to spread out and search the top levels first, and then it's going to search the next level after that, and then the next level after that. Right? To do this algorithm, we're going to need something called a queue data structure. You may remember that in the depth first search algorithm, we used a stack where we added data onto it, and then we were removing data from it. Same thing here. We're going to use a queue data structure, and it turns out that because of this queue, it allows us to sort of do this breadth first search where we can search the next layers of nodes, in this sort of order that we're kind of looking for. So how would we do this with with a queue data structure? Now, remember that a queue data structure can be implemented using a list or a vector, whatever you want to use, or you could build your own custom queue data structure, which would have some performance gains over either of those. But the important thing is that as we add data onto it, it's going to remove data from the bottom of it, right, or the front of the line, right? A queue has the same operations as a stack. It has a push and a pop operation. But when you are removing data from it, it takes the elements that have been in the queue the longest, right? This is just like the line that you're waiting, in at the grocery store, or the line that you're waiting in when you get to the toll booth. You pull up, or at the drive-in, right? So you pull up in your car, and whoever's been there the longest is going to be the next person to get served. So the way the breadth first search would work is we're going to build this in an iterative way. So we are going to be exploring these nodes one by one, and we want to make sure that we traverse down this hierarchy at each depth level in order. So we're going to have this node that we're exploring. We'll just call it N. And the first thing we want to do is we want to take our root node, and this is just like with depth first search. We want to take our root node and we want to add it into this queue data structure. So we add our first node, into this queue data structure. Then we would start our iterative process. So the iterative process would essentially say, let's go remove the next element from this queue. Right now I'd be removing the element 1. The node we are currently exploring is node 1, and this would be removed from the queue. Then we would add nodes 2 and 3 into our queue. 2 and 3, right? Now we've got 2 elements here in our queue waiting. And then the 1 would essentially be replaced by the next element in this queue, right? So we do the next iteration of our loop, and we'd say, what is the next element that we should explore? And remember, with this queue data structure, it's going to look at the element at the bottom. It's going to look at the element that's been in here the longest. So 2 has been in here the longest. So we're going to remove 2, and the element that we're currently exploring is going to be element number 2. Now element 2 is going to add 4 and 5, right? So as it adds elements 4 and 5, it's going to put them here into our queue, 4 and 5. And then we're going to go to the next iteration of this loop, and we're going to take a look at the next element that's going to come out, which is going to be this one here, the one that's been here the longest, which is the 3, right? So note that we started with element 1, and then we went to element 2, and now we're about to explore element 3. So we pop the next element off of our queue data structure, which is the element 3, and gets updated to 3. and now we're sort of exploring 3, 1, 2, 3, right? So we're sort of traversing downward by depth, right? Notice we are not exploring 4 or 5 yet. 3 would add 6 into the queue, right? 6 gets added into the queue, and then we're finished exploring 3, so we're going to update to the next node. The next node that we want to explore is 4, right? So we went 1, 2, 3, and now we're going to hop all the way back over here to the 4. Even though it's on a completely different branch down this tree, it is the next node on the next level of depth. So we remove the 4. The 4 gets updated as the node that we were currently exploring. And so we were going 1, 2, 3, 4, and then we would continue. 4 has no children, nothing would get added here. We would then explore the 5, and then we would finally explore the 6. So this would end up looking something like this: 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It's exploring it level by level down. This is the fundamental difference between a breadth first search and a depth first search. So let's look at the pseudocode for a breadth first search. Now we did this iteratively, and we're going to continue doing that. So the thing that we need here is a queue data structure. This is going to look very familiar to the pseudocode for the depth first search. The biggest difference here is just how this queue operates. So remember, the queue can be implemented using a vector or a linked list, or you create your own custom queue data structure. The purpose of this is that there's going to be 2 functions that we're going to use. It's going to be a push, which adds data onto it, and a pop, which takes the next element off of it based on the order in which they were put onto the queue. Then we have the current node that we're exploring. So this is a node in our tree, and we'll just call this N. That's the one we're currently exploring. And the first thing we need to do is add our root node into this collection of next nodes. We're going to push the root node onto this, and then we're going to start our iteration. We're going to say, while the next nodes is not empty, while we haven't explored the entire tree, we're going to keep looping, right? And then inside this loop, we're going to say that N is equal to next node.pop. We're going to remove the next element from the queue, set that to be the element that we were currently exploring, or the node that we're currently exploring. Then we're going to add all of the child nodes of N into our queue data structure. So we need to do something like this. We need to say next node dot push and dot right, next node dot push and dot left, right? Now remember, this is just for a binary tree. Essentially what you're doing here is you're adding every single child node of N into the tree. So this can work with trees that have 8 children or N number of children. You just need to make sure that you're adding each child node into the queue data structure at this point. For our purposes here, we're just looking at a binary tree, so there's just a right and a left. That's it. And that's it. This does our traversal. The last thing that we would need to do is, well, this is a search, so we're searching for a piece of data, and we would do that probably right here. We'd say if N, the value of N, is equal to whatever value that we're searching for, X, then we can return true. And then if we get through our entire while loop and we traverse the entire tree, then we can return false. We've explored the entire thing. We know that it doesn't exist. Now, if you go take a look at the pseudocode for the depth first search, you probably notice that this entire thing is exactly the same. The only thing that's different is this queue data structure. So the data structure has a huge role on the way that we are traversing this tree. And that's really important to know. With a breadth first search algorithm, you want to use a queue data structure. With a depth first search algorithm, you want to use a stack data structure.